Hey there, guys. I hope everybody's doing well and taking care of themselves. With this new week that we are starting, we are moving on to a new unit. We're taking a look at Unit 2. And we've got 3 lessons that are going to be due this week. And so whenever you look at it on the spreadsheet, this is what it looks like. And I've changed it from it being like an everyday type of you have to do this day, kind of like I had for the last couple of weeks. I'm just giving you the lessons that I want you to work on. And if you want to get them all done all at once, that's fine. If you want to do one this day and then procrastinate and do it those days, not my favorite, but also okay. So you just need to do what works with you and your schedule to be able to get the stuff done. You will also see on the spreadsheet that I do have the days of the weeks, and looks like I need to fix them over there. No, they're good. But looking here, you're going to see Ms. Schaefer's and my virtual office hours. These are times when we are online live for us to be able to help you. So like you can log on if you're stuck or if you just want to hang out. Either way, we'd love to hang out with you for a little bit and be able to have a chance to say hi because we miss you guys. But yeah, you can share your screen with us, show us what you're seeing, show us what you're stuck on, and have us help you get unstuck. Okay, so looking at the curriculum for this week, looking at Unit 2, there's three different things to work with the first lesson, 3 for the second, and 3 for the third. The big things that we are going to be super worried about and focusing on for our completion grades is these mastery tests kind of a thing. So we're looking for you to do whatever you need to do. If you need to go through the tutorial and work your way through the tutorial, do that. If you need to work all the way through the practice, do that. If you know the stuff well enough and you can feel you can take the mastery test and do okay, that's okay too. I will warn you, if you go in here and you get it locked, you do got to work through this other stuff in order to be able to get it unlocked. So make sure you understand what's going on and you're pretty confident with material before you go in here and get yourself locked and have to go through every bit and piece of everything. Okay? All right, looking at this first lesson that we're working with, we're looking at modeling and interpreting with linear and exponential functions. The linear part is going to be review. The exponential part, some pieces of it are going to be new, okay? So if we take a look at things in the document that I made, if we're looking at a linear function, we've done lots of work with these. It's anything that has the shape of a line or anything in the form of f of x. Remember, f of x is just another way to say y. F of x is equal to mx plus b, where m is our slope or the constant change. So like if you look at your step and go from one step to another, the numbers are changing by the same amount every single time. So like they're going by ones or they're going by twos, each column is changing the same. And then if there's a constant increase in whatever your problem you're working with, so the numbers are increasing the same every time, the problem is going to have a positive slope, and so the number up here is going to be a positive whatever's going on. If there's a constant decrease in the problem, then the slope right here, the number m, is going to be negative. And a friendly reminder, looking at our formula for slope, m is equal to rise over 1 or rise over run, or y2 minus y1 divided by x2 minus x1. And then with working in the tables, another way you can do this is you can do the second term minus the first term, find out what that common difference is. And then you've got to check all of them, though, because just because you get one doesn't mean they're all going to be the same, because we also have a second type that we can work with, which is exponential. So you've got to check all of them. And that's one way to tell the difference between exponential and linear. So you also have to do like the third time minus the second term and then keep going through that. And then, of course, your b is your y-intercept, and it's the value that you're going to have at time is equal to 0. The other type of function that we're going to have are exponential functions. F of x is equal to a. A is the initial value that you start with in whatever problem or situation that you have. And then times the quantity 1 plus r to the x power. R is going to be the rate of change, and it's going to be either measured in a decimal or percent, and it can be found is the way they are usually presenting them to in problems. So if you're working with any kind of problem and it's talking about things doubling or increasing by 5%, those kinds of things, those are going to be your exponential functions. You can so if you do the subtraction that I was talking about up here and the numbers are not the same, and another way that you can work with the numbers is to take that second term divided by the first term, and then the third term divided by the second term, and find it that way. And we'll do examples of what those looks like. I forgot to put the x in here. Your x is equal to time, whatever time you're working with. And you've got to be careful and read your problem to see whether it's talking to you about years, months, those types of things. So looking at this 1 plus r, so I feel like the a and the x, it's kind of pretty self-explanatory, but that 1 plus r is a little bit different. So that's where you're looking at whether or not your problem increases or decreases. So if we're looking at like an r is equal to 0, so there's 0% change. So I started with this one because this is kind of like the median where everything starts. This is what you have. So you would take that and you have 1 plus 0, which would give us a decimal of 1.0. Or if you were looking at a percent, it would be 100%. So with this, there's no change to whatever is going on. Everything's staying the same. This is the place where we're starting. And then they could do other types of R values. So they could tell you that the R value is equal to 0.25. Or they could say that there is an increase of 25%. So that's a positive number. So I would put in here a positive 0.25, add those together, and we would get 1.25. Or if we're looking at our percent, it's 125%. So we could do another example of an increase, 0.73. This would be another increase of an R value of 0.73. So you would just put the 0.73 in here. And this way you would be doing it in your math or whenever you're working out your problem. So 0.73, and this would be 173%. And then you can have R values bigger. You can have R values of 2. This is still an increase. And then you're doing 1 plus 2, which will give you 3 as a decimal, or an increase of 300%. So basically it increased 3 times what it was. So then we're looking at, well, what happens if we're looking for decreases? So with these R values, they're typically, you're going to put a negative in front of them because they're a negative change. So we're looking at like negative 0.25. So something decreases by 25%. So we would plug in a negative 0.25 here. We would do the 1 plus 0.25. So that decimal that we would be working with is 0.75. So if something decreases by 25% or 0.25, we're looking at 75% of what we originally started with. So if we look at another type of decrease, looking at our value of negative because it's a decrease, let's go 0.48. So we would have to go in here and put our negative 0.48 in there. And then do 1 plus a negative 0.48 or 1 minus 0.48. And that'll give us 0.52 as our decimal, or 52% of what we started with. And this can go all the way down to like 0.99 is usually as low as, that they'll go. I mean, technically they could go lower. I don't see them doing that here, negative 0.99. It should be a negative here because it's a decrease. And then that'll give us a decimal of 0.01 or 1%. You typically can't go negative whenever you're looking at these types of things. Okay, so this kind of gives you a feel of what that 1 plus r is going to do whenever we're looking at our equations. All right, so now that we've got kind of an outline of what we're looking at, let's go ahead and take a look at, I'm looking at these practice problems and working these practice problems out with you. So looking at the first question, they tell us that we've got a cell phone carrier introduced a new strategy to increase the number of their subscribers. The function below represents an increase, so important words we want to pick out and think about, increase in the number of subscribers, where f of t represents the number of subscribers, And T, this is the time that I talked about, they used X whenever we looked at it in our equation over here. They used X. Here they're using T for us to help remind us that it's time, represents the time in months. So looking at the form, comparing to the y's f of x is equal to mx plus b, that form versus this form, this is going to be an exponential function because it has a number times another number to an exponent. It's got an exponential or exponent variable in it, and that's how we know it's an exponential equation. So we've just got to use our basic form of equation and match things up. So if we're looking at this, we've got 250 is out in front. That is our A value. It's the initial value. Where are we going to start with the problem or situation? So looking at the drop-down boxes, it tells us the cell phone carrier had blank subscribers before the strategy was introduced. So we're looking for everything started. Everything started at 250 subscribers. And then every blank after the new strategy was introduced. So these are increments of time. So this is where focusing on this, it was so important. So it's going to be every 1 month that things are going to change. The number of subscribers increase by a factor of, so when we're looking for increase by a factor of, that's what this number on the inside, that is the factor that changes our initial value that we started with, and it's going to be a factor of 1.4. Okay, looking at the second question. For this one, they want us to drag each table of values to the correct location on the chart, determine if the values in each table can be represented by a linear or an exponential function, place each table in the correct location on the given chart based on its classification. So this is kind of a matching thing. We're looking for things that are linear or make a straight line, and then we're looking for things that are exponential and make that curve. So looking down here, I'm going to check all my X values and make sure that for each of those tables that I'm looking at, they're each increasing by the same amount for the X values, and that way all I need to do is focus on my Y values. So if I look at what I've got, it's going 0, 2, 4. This one's going up by 2s, -3, -2, -1. This one is increasing by 1s. -1 to -4 is subtracting 3, and then this one's increasing by 1. So my X values are consistent, so it's going to make it easier for us to be able to figure out which one is going to be exponential or linear. There's not going to be a lot of extra work for us to do. So if I start with the nicest looking one to do for an example, remember I told you our focus was going to be on subtracting first to figure out if there was a common difference, and then if there wasn't, I would be dividing. And that's what I'm going to be doing with these numbers. So if I take a look, and I look from, I'm going to do 16 minus 8. We're going to take that second number and subtract the first one from it, and that's going to give us a difference of 8. And then I'm going to do the same thing. I'm going to do 32 minus 16. I grab my calculator and check that out. 32 minus 16. That will give me 16. So this is not a linear function, because if it was, these two numbers would be exactly the same. So it's not linear, so it's got to be exponential, but just to show you what an exponential function looks like, just so you know math-wise what you're looking for. Since the subtraction method didn't work, to get the same number, we're going to do the division. So I'm going to do 16 divided by 8, and that's going to give us 2. And then I'm going to do the third one divided by the second one. So 32 divided by 16, that's going to give us 2. So this is and this is going to lead into what we're doing in some of the other lessons. I'm just going ahead and using the vocabulary for you now. We have a common ratio of 2. So that makes this one be exponential. So I'm going to take this one and put it in our exponential column. So then looking at the other ones, I don't know, how about this one next? It has less fractions than what is left. So I'm going to hit clear. And then trying out the second minus the first. So 2 minus 6 will give me a -4. And then 2/3 minus 2, that does not give us a constant number. So with this, I got negative 1.3 repeating. So this isn't going to be linear. It's going to be exponential, math-wise what you're looking for. I'm going to take this second number and then divide it by first. So 2 divided by 6 gives us 1/3 or 0.3 repeating. And then that 2/3 divided by 2. So 2 divided by 3 divided by 2 is going to give us 0.3 repeating again. So because these two numbers are the same and we use the division to find a number that is the same, that common ratio, that is also going to be an exponential function. So I'm going to take this guy, grab it up into our exponential functions. So then with these, I'm going to take them and put them straight into my calculator. If I do 7/4 minus a negative, don't forget to put that negative in your calculator, 5/4, that'll give me 3. So my common difference, that's the word we use, is for between those two is going to be 3. So now I'm going to do 19/4 divided by 7/4. No, sorry, minus 7/4. And that is also going to give me 3. So since using the subtraction method, I was able to get the same number or that common difference, that makes this be a table for a linear equation. So now looking at this guy over here, do the same method, negative 3/4 minus 3/2. That's going to give me a negative 2.25. And then I need to do negative 3 minus negative 3 divided by 4. And that's going to give me a negative 2.25 again. So while I'm doing these, make sure that you're putting them in your calculator as well, and make sure you're getting the same answers that match mine. That way, whenever you end up doing the problems on your own in that mastery test, you know that you're typing them in correctly, or you've already caught yourself to, if you are making mistakes. And that way, you're not missing it because of typing in your calculator incorrectly. Okay? All right, so that is looking at question 2. Looking at question 3, the table below shows a function f which represents the depth of the sea x feet from the coast. And you take a look, we've got our table that they gave you. Which function represents the situation? And if you look at what they give us all linear equations. So we don't have to make the decision about whether this is a linear function versus an exponential function. We just need to be able to match what's going on. So there's a lot of different ways that we can solve this. I'm going to use our y is equal to mx plus b information. So looking for the slope, we're going to use that slope formula. So I'm going to pick these two right here. Normally we would have to check to make sure whether it's linear or exponential, but we're good with this one. So I'm going to do 7 minus 1 for my y values divided by 3 minus 0. So 7 minus 1 is 6 divided by 3 is going to be 2. So my slope is going to be 2, and this is a positive 2. And if you look, if you're not sure, these two are the only two equations that have a 2 in it. If you're not sure whether your slope is positive or negative, look at the values. If these values are increasing and going up to be positive and bigger numbers, and these values are going positive up to be positive values, that's going to make your slope be positive. And so that will make this equation, just to double check, our y-intercept is 0, 1. So there's our plus 1. So that will make our equation be f of x is equal to 2x plus 1. Looking at question 4, in 2010, there were 400 frogs in the lake at a local nature preserve. Each year, the population of the frogs grows by 10%. So this is important. It's growing, so that you need to be looking out for words that are increasing and decreasing. Another hint for the type of, besides what they give you in the multiple choice, but another hint for what this function is going to be between it being linear versus exponential is the fact that they use a percent. If they've used a percent, it's going to be at some type of exponential growth. So it grows by 10%, which equation accurately describes the population of frogs f of x years after 2010. So if we take this equation and we look at I'm going to be looking at our exponential function that we have right there. Let me see if I can't make it a little bigger, make it easier for you guys to see. There we go. So if we take this and we take the information and plug it in, we know that our A represents the initial value. So we need to go and find the initial number of frogs that they started with. So if you look, there were 400 frogs to start with at the nature preserve. So instead of an A, I'm going to have 400. My f of x is going to stay the same. This is not something that I need to plug things in for, times 1 plus, and then I need to have a value for r. So we need to find our rate out of the problem. So we've got a population of frogs growing by 10%. So we can't take that 10% and just put it in right here. We've got to switch that to a decimal because we're not using this 1 here is not a percent. So whenever we take that rate of 10, we've got to plug it in as a decimal. So move the decimal spot over 2 spots to the left, and that'll give us the 0.10, and then they're using x for this. So then all we need to do is simplify what we've got right here in our parentheses. So we're looking at f of x is going to be equal to 400 times 1 plus 0.10 is going to be 1.10 to the x. So that'll make that answer be that one right there. Okay. Looking at 5, this one is going to be a linear change. So we've got a party hall, because the answers they give us to work with. A party hall is renting chairs for an event. The cost to rent each chair is $5 and the delivery charge is $50. So because there's an exact value, when they say the cost to rent each chair is $5. So you could say, well, if I rent 1, it would be exactly this. If I rented 2, it would be exactly this. You can figure out what the value is without having to know the one before. That's what makes this one be linear. So if f of x is the total cost for renting chairs, which of the following linear functions model the situation? So if we're looking, it's $5 per chair, so that's going to be 5x. So that automatically eliminates those three for us, just to double check and make sure we're picking the right one. The delivery charge, the one-time fee, is going to be $50. So that just confirms for us that that's going to be that equation right there. Okay. Looking at question 6. This one wants us to select each situation in which one quantity is changing at a constant rate in relation to the other quantity. So we're looking, again, for exact. No percents, no doubles, no triples, none of those words where we would have to have an initial value to be able to start and figure out what things are. So Harry rides his bike at a speed of 20 miles per hour. That's going to not change, and that is going to be constant the whole entire time that we're looking at the problem. Zion's salary increases 2%. There's that 2%. That is not, while it is a constant rate, the amount that it gains every year is going to change and get bigger and bigger. And that's not what we want. We want just the same amount that it would get bigger. So it would need to say salary increases by $200 a year, something that is the same no matter what year it is. Looking at the next one, go-kart rides cost $2 each. That is constant, not changing. Every hour, 35 gallons is drained from the pool. Same amount over over time. So that is also a constant. And here's that word doubles. Anytime they're talking about doubling, tripling, quadrupling, or cutting it by a quarter every so often, those types of things, those are exponential. And then Jade earns $5 for every apple pie that she sells. This is another constant. Every pie she sells, she knows she's getting $5 no matter what's happening. So those are our answers that increase or change at a constant rate. Looking at 7, they want us to select the situation in which one quality is changing at a constant rate in relation to another quantity. So with this one, we've got a decelerating body covers half the distance to its destination each second. So this one's exponential because let's say it's 10 feet away. Half the distance would be 5. And then half the distance of that 5 would be 2.5. And then half of that 2.5 would be like 1.75 or something like that. It's not the same amount that it decelerates over a period of time. So that makes that one be exponential. Ryan runs 3 miles a day. Doesn't matter what day, it's going to be 3. There's that 1.5% that would be exponential. And then population of rabbits doubles. There's another one of those keywords that tells us we're looking at an exponential change. So we're looking at the one situation constant rate would be Ryan runs 3 miles daily. Taking a look at 8. The function below describes the population of fish in a river, where f of t represents the number of fish and t represents the time in years. So I've got f of t is equal to 200 times 1.1 to the t power. So what information can be interpreted from this function? So if we write this down, so I've written it down, and I've written our original definition function right above the function that we're working with. So if I match up the things, I've got my A is equal to 200, and then I've got my 1 plus R. 1 plus R is equal to 1.1. So if I wanted to solve for R and know exactly what my rate was, I could subtract the 1 from both sides, and then I would have 0.1 left over, which if I switch that to a percent is 10%, and then our times match up right there. So looking at this, every year the population increases by a factor of 1.1, which is what's happening. This is increasing by a factor of 1.1. Every t years, no, because it says time represents, t represents time in years. It's not 2 years or 5 years. So that one's not going to work. And then every 1.1 years, if that had been the case, it would have been 1.1 up there. And then every year the population increases by a factor of t. If that would have been the case, we would have had to have a t there. So we're looking at every year the population increases by a factor of 1.1. Looking at 9, we've got a local music festival has gained popularity since 2000. In 2000, 760 people attended the festival. In 2001, 1,140 people attended the festival. In 2002, 1,710 people attended the festival, and in 2003, 2,565 people attended the festival. Which statement best describes the situation? So I'm going to kind of break down those sentences into little bitty pieces and not worry about the sentences all at once. So I'm looking for that first phrase that's kind of the same throughout all of them. And I'm looking at an increasing exponential function. So that's versus a decreasing linear exponential or a linear function. A decreasing exponential function and an increasing linear function. So that's a decision that we can make first. We can make the decision of whether or not we're looking at exponential or linear. And the way that I like to do this is I like to write the information down that I'm working with, and I'll be right back as soon as I've got it up there. Okay, so now I've got to make that decision between whether this is going to be linear or exponential. The very first thing I always want to check to make sure is to see whether my x values are increasing in the same amount. If they are, then all I need to do is focus on my y's. If there aren't, I would want to use something like the slope formula to try things out and see how that would work. But we're lucky this increases by 1s, so we can use our subtraction method to be able to figure things out. So if I subtract 1,001, or if I do 1,140 minus 760. So right now what I'm trying to figure out is, do I have a linear function? So I'm going to do like b minus a. So that second term minus the first term. So I'm doing 1,140 minus 760, and that gives me 380. So then I'm going to do the same thing here. I'm going to do 1,710 subtract 1,140. And when I do that, I get 570. If this were a linear function, then these numbers should be exactly the same. So because right here to there, they're not the same, automatically, no, this is not going to be a linear function. I don't need to go and check these two because it doesn't matter what they are. It doesn't even matter if this one is 570 or if it's 380 and it matches with either of those two, because not all of them match. This is not going to be linear. So that means it's got to be exponential. But to just go ahead and show you the math so you can see what that looks like, this is going to be like a b divided by a, or that second term divided by a first term. So I'm going to take 1,140 and divide it by 760. And if I put that in my calculator, I get 1.5. And then if I do the same thing, 1,710 divided by 1,140, I also get 1.5. And then I like to check all of them just to make sure, and they didn't put some kind of a sneaky problem in there on me. 1,710, put that in the calculator and divide it out, and that will give me 1.5 as well. So this tells me that yes, this is going to be an exponential function. So with that in mind, I'm going to go through, and we've got exponential, so I'm going to say it can't be this one, and it can't be this one. Okie doke. So then I need to decide whether it's an increasing or decreasing. So if we're looking at increasing, remember we talked about this on our table. If we're looking at values that are increasing, it's going to be 1 point something, 2 point something, 3 point something. If we're looking at decreasing, we're going to have these numbers, these decimals that are less than 1 that we're finding. These numbers right there is the numbers that we're finding there. So because we've got numbers that are bigger than 1, that means it's going to be an increasing exponential function. So that makes it be this one right here. And so just those two words help decide what it was going to be without us having to worry about what was in the rest of it. All right, looking at 10. 10 has us doing a study revealed that the volume of runoff water flowing through a stream is increasing due to global warming. The average annual volume of runoff in thousands of cubic feet in years after the study was conducted and is modeled by the function below. The parameter B is an unknown positive base. So they don't know for sure how much it's increasing or decreasing. They know it's increasing. They just don't know how much by. So then which statement is going to be true about our situation? So looking at the first option that they give us, if B is equal to 1.2, the annual growth rate in the volume of runoff water flowing through the stream will double in 5 years. We don't have quite enough to work with that one. If B is equal to 1.5, the annual growth rate in the volume of runoff water flowing through the stream is 115%. Still, same thing there. Based on the model, the average volume runoff water when the study initially conducted was 1,869,000 cubic feet. Yeah, that's what it is. Like whenever everything started, remember that A value, A times 1 plus R to the T or N or X. This is our initial value. So that's the statement that we know for sure 100% is true based on this situation. Looking at 11, we've got two ordered pairs, 3, 2, and -2, 13 are points on our linear function. Which equation best describes this function? So this is going to be one of those problems where we've got to use our slope formula to figure out what's going on. So remember our slope is y2 minus y1 divided by x2 minus x1. So if I'm looking, my y2 value is 13 minus 2, or my y value, so just the second one. So there's my 13 and there's my 2. And then negative 2 minus 3. So 13 minus 2 is going to be 11, and negative 2 minus 3 is going to be a negative 5. So that's going to be our slope. That's going to be our m value. So looking at what we've got, this is the only one that's got the negative 11/5 value. So that is going to be our equation, the equation that best describes the function that goes through those 2 points. Looking at 12, Tricia compared the number of birds of a particular species in 2 sanctuaries. The results are shown in the table below. So we've got our time in months, 0, 1, 2, 3, 4. We've got the number of birds in the sanctuary, 3, 6, 12, 24, 48. And then they give us a list for number of birds in sanctuary 2. Which statement best describes the situation? So the number of birds are in neither sanctuary are changing exponentially. Only the number of birds in sanctuary 1 are changing exponentially. The number of birds in both are exponential. The 2 is the only one changing exponentially. So we've got to figure out, look at both of these graphs, or both columns of numbers, and figure out which one are going to be exponential. We don't need to check them for linear. It's not an option we need to worry about. So I'm going to use that method, and if I do where I do like the b divided by a, the second term, or divided by the term, or a term divided by the term before it. So if I do 6 divided by 3, that gives me 2. If I do 12 divided by 6, also gives me 2. 24 divided by 12 gives me 2. And then 48 divided by 24, that also gives me 2. So sanctuary 1, that one is exponential. So then if I look over at the next one over here, I'm going to do 18 divided by 10. That'll simplify down to 9/5. With these, whenever you can, make sure you're simplifying them down, because you don't want to assume. I mean, I had 6/3 over 12/6. Those do not look exactly the same, but whenever I simplify it down to 2, they are the same. So make sure that you're simplifying them down to either the most reduced form of the fraction, or just switch it to decimals to make sure the decimals are the same. I would take it out at least 3-ish to maybe 4 spots. That way you don't end up with something like 0.0213 4 for one and 0.0213 for another, because those would not be the same. So just be careful with those. And then so here, if I do 22 over 18, that's going to be 11/9. So 11/9 and 9/5 are not the same. So sanctuary 2 is not exponential. So I just go find the one that says the only number of birds in sanctuary, the only number of birds, only the number of birds in sanctuary 1 is changing exponentially. So there we go for 12. Looking at 13. So using the table of values below, select the correct statement. So checking my table, 0, 2, 4, 6, 8, 3, 12. These aren't going by one, so we've got to be careful with whatever number we're looking at. We've got to figure out, if I read just the first little phrase to start with, the very first decision I can make is, do I have an exponential or a linear function? So let me get that up on the board so I can play with it, and I'll be right back. Okay, so making that linear decision. So that's going to be the term minus the term before it. So if I do 12 minus 3, that's going to give us 9. 48 minus 12, that's going to be 36. Yeah, definitely not going to be linear. So that lets me automatically eliminate not linear, not linear. is growing by equal factors over equal intervals. So we need to figure out whether it's 400% and 200%. And this is where you got to be super careful. You can't just go, well, because this is a constant increase, I can go from there and say, well, this is going to be 3 times 4 to give us 12 times 4 times 4, because this isn't increasing by ones. So I to be safe, I like to do my slope formula just to double check. So 12 minus 3, because these are my y values, 12 minus 3 is going to give me 9 divided by 2 minus 0. So that's going to give me 9 halves. So 9 divided by 2. Did I do that right? Hold on. Okay, I got it. This didn't work out because it's not linear. We're looking at exponential. My bad. So I can't use slope on that guy. I've got to look at the changes that I have here. This is increasing times 4. 12 divided by 3 gives me 4. 48 divided by 12 gives me 4. And I could check all the others, but it's still going to multiply it by 4. So then what I need to do is, we're looking at from here on, this is increasing by 2s. So I need to take that 4 divided by 2, and that will give me my rate of change is going to be equal to 2. Or if we look and we switch it to percents the way they want us to, it's going to be 200%. So that's going to make the answer for 13 be this guy right there. Looking at 14, the height reached by a ball bouncing on the floor decreases by each bounce. The function that describes the height h in meters after x bounces is given, where b is the unknown positive case. Select the correct statement. Okay, so I took all the choices that we had and I got them up on the board. And it's just a matter of playing with that b value or that 1 plus r to make sure that we understand how things go into that value correctly. So if we're looking, the way that we can figure out what this r value is based on these b values, we could just set up little equations to solve. So like 0.79 is going to be equal to 1 plus r. And then we can solve and see if we get the numbers to match those. So if we're looking and I subtract 1 from both sides here, I'm going to do the 0.79 minus 1, and that will give me a negative 0.21. So if I'm looking, this is a decimal. If I switch it to a percent, it's negative 21%. So to translate what this is saying is this negative means I'm going to have a decrease of 21%. So it seems like right off the bat, this one's going to be our answer. But just to go through and kind of work through the logic of the rest of them, this one is b is equal to 1.04, and it's a decrease of 40%. Remember when we talked about in our table, and I can switch back to our table, when we were looking at these, anything that has like a 1 point, 2 point, 3 point, those are all going to be increases. So automatically, I'm going to go and say that neither of those are going to work and not bother with the math with them, because this can't happen. We can't have a 1 point something and have it be a decrease. A 1 point something is always going to be an increase no matter what you're working with. So this is just an untrue statement for both of those. So the only possibility left is going to be this last one that we have here. So if I do the same thing and say, okay, I want to see this b value that I have, 0.83 is equal to 1 plus r. Subtract the 1 from both sides. So 1 minus 0.83. And that's going to give me 0.17 is going to give me my R. And that's not, if it's my B value is 83, it's going to be a decrease of 17%. So looking at that one's not going to be it. So the very first one that we were looking at for that problem, this guy right here, the 0.79 is a decrease of 21%. That's going to be our answer for 14. Okie dokie, last one, question 15. Drag each situation to the correct location on the table. Classify each situation as exponential growth or exponential decay. So looking between the difference between growth and decay. Whenever we're looking at these, growth, we're looking for things like increase, those types of things. Decay is decrease. So we'll play with these and take a look at them. So monthly sales of albums by a band whose populating is declining. Declining means whatever is happening is going down. So that is going to be an exponential decrease. The amount of a radioactive element remaining in a sample every decade. Whenever we're looking at radioactive elements, as soon as they're created and as soon as they automatically start to decay over time. The value of a home in a growing community. There's one of those hint words. Growing is an increase, so that's going to be increase. The amount of money in a savings account that earns interest. Earns, that's an increase word, so it goes in this column, in our growth column. And then the temperature of a hot cup of coffee left on the counter every minute. So this is one of those, you kind of got to know what's going on, situation kind of things. Coffee's going to cool off. The temperature is going to go down. So that's going to be a decrease or a type of decay that is happening. All right, so that's my walkthrough that I have for you for this first lesson. I know it's kind of long, but they gave you 15 examples for you to work with, look through, using this video to help you understand. Hopefully this has helped. If it has not, feel free to email either Ms. Schaefer or I, and we'll be happy to get back to you. Also, you can pop into these office hours that we've got up here. Around the time my links go live, if something happens like with our kids and we can't make it, we will change the hours on here, or we'll let the other know so that they can change the hours. But yeah, you can see through the whole time this has been going on, I've only had to change, Ms. Schaefer's been good, but I've only had to change my hours once because of stuff that was going on. So we're here pretty consistently every single day for you to help you through this stuff and understand what's going on. Okay. If you got any questions, let us know. Otherwise, take care. We miss you guys.